This question is taken from the January 2026 paper. This is question 10. Your question 10 is always on vectors and matrices. So the first question here, the diagram below shows triangle OPR. The point M is the midpoint of OP, and the point N is the midpoint of OR. In the diagram, OM is equal to U and ON is equal to V. So before we go on to the questions, we can immediately identify something. And that is that if M is the midpoint of OP, it means that M divides the whole line or the whole vector OP into two equal halves. That's what midpoint means. The midpoint of any line divides the line into two equal halves. So in other words, OM is equal to MP, right? So if OM, the position vector, OM is U, then MP, which is the other half of the entire line there, will be U as well. So that means that MP is also U. And I'm putting that in one time before I go to read the questions. So just like with the circle theorems, you know how we identified as many angles as we could possibly identify before we even went to read the questions. It's the same thing that you should do with your vectors diagrams. Identify what you can before you go on to the questions, right? So ON, likewise, N is the midpoint of the entire line OP. Let me just highlight what line I'm talking about, what vector I'm talking about. The vector ON is the position vector here. OR, sorry, right? That's the entire vector OR. Position vectors are vectors that begin at the origin, right? So O is the origin. Right, so if N is the midpoint of OR, it therefore means that at this point here, right, these two are equal halves. So therefore, ON, right, ON from right here, ON, right, will be equal to NR because N is the midpoint of the entire line. So just like with OM being equal to MP, then ONR is also equal to V, right? And so we can therefore say that the entire vector OP will be equal to U plus U. So the entire vector, the entire position vector OP is equal to 2U. And the entire position vector OR is equal to 2V, right? Because it will be, OP would be equal to this distance, OM plus OU, which gives me, so plus MU, sorry, which is U plus U. And so it's the same applies for OR. So you have 2U and 2V. So now let's go on to the first question. It says find, in terms of U and V, simplified expressions for MN. So guys, this is the triangle rule of vectors, right? The triangle rule of vectors says that if I want this vector MN in this direction, I must start from M. So I'll go from MO and then add ON. So the position rule of, the triangle rule of vectors is that this resultant vector MN can be found by adding this vector MO and then ON. So that's one thing to note here. The other thing to note is that when you reverse the direction of a vector, the sign changes. So if OM is equal, right? So if, oops, let me take off that. Right, so first things first, part A, it says to find in terms of U and V, the simplified expression for MN. Remember, to get mn, you first have to look at your diagram to see how to get it, right? Mn could be many different ways you can get mn, by the way. You could get mn, this vector mn, you can get it by adding mp to pn. That's one way to do it. Or you can even say, to get mn, I will add mp, pr, and then rn. That's also another way that you could get mn. However, I don't know what pr is, and I didn't know what pn is either. So it makes sense to simply use what is given to us there, right? Which is we have om and we have on. So some things to note here is that if you have to find the vector mn, you need to start with m. You have to start at that point m, and you have to end at the point n. So you would have to say mo plus on. So look at some things here to note. You starting, because you want the vector mn, you have to start with m and end with n. Likewise, the point in the middle is the same, right? Because it's one continuous movement. It's one continuous movement. You're going from m to o and then from o to n, and that gives you the resultant vector mn. So that is something to pay very close attention to, all right? So now we know that OM is equal to U, right? That was given to us. OM in this direction is equal to OU. So if I want MO instead, OM is equal to U. So if I want MO, that is going in the opposite direction. And since it's going in the opposite direction, you will change the sign of U. So it will actually be minus U. All right. And while ON is given to us already, it's just V. So ON is V. And therefore, the vector MN in terms of U and V will be minus U plus V. Or you could put V minus U. Doesn't matter how you write it, but it does matter which signs you use. So that's the first thing. All of the things that I just discussed with you are things that you have to know when you are approaching a vectors question. The first thing was that the direction matters. Well, that wasn't the first thing, but it's just one of the things. The direction matters, right? So if you have the vector OM is equal to U, then the vector MO will be minus U. Likewise, if you have the vector ON in this direction, starting at O and ending at N, if it is V, then NO will be minus V. Very, very important. The direction matters with vectors because a vector quantity includes the size and direction. A scalar quantity is just a number, right? So like 2, 4, half, any number. But a vector quantity has both size and direction. All right. Another thing that we looked at here is that if you have the midpoint of a vector, it means that point will divide the vector into two equal vectors. So therefore, if you know that OM is equal to U, and M is the midpoint of the entire vector OP, then MP will also be equal to U. So the entire vector will be this plus this, or you could say U times 2, which will give you 2U. Similarly for OR, right? N was the midpoint of OR, so ON is equal to V. That means that NR on that same line is also equal to V. So the entire vector OR is 2V. So those are things to note, all right? And then the next thing is if you have to find the vector MN, it means you have to start at M and end at N in one continuous movement. So if you're going for MN, you'd have to go OMO plus ON. So that's one mark. The second question is to find the vector NP. So to find the vector NP, well, NP is this vector here. So to get to NP, I will say, I could say, there are two ways I could get it. I can do NR plus RP, because that starts with N and ends with P at one continuous one common point R. That's one way. Or the next way I could get to NP would be to go from NM to MP, right? NM to N to MP. So let's write that down. That's part B. So to get NP, NP would be equal to, I decided to say it's NM plus MP. And the reason I chose that direction, guys, is because in the first part of the question, I already found what MN was equal to. MN is equal to negative U plus V. So that means NM, which is the opposite direction, I would have to change the signs here, right? So NM will be equal to, instead of minus U, it will be plus U. And instead of plus V, it will be minus V. So NM will be equal to U minus V, and then MP is already given. Well, we already deduced what MP is. It's U. So this will be U minus V plus U. And so the entire this would just be 2U minus V for NP. Right? So that's one way. Another way, guys, that you could have found NP, let me show you as well. NP could have also been found by saying NO, which will be minus V, plus OP, which is 2U. So do you see it's the same answer, right? It's the same answer that you get, 2U minus V. Let's write that down as well. It could have also been, this could have also been NO plus OP. That would have given us NP as well. So NO is minus V because it's in the opposite direction of ON. So if ON is V, then NO will be minus V. And OP, we got that up here, is 2U. So minus V plus 2U, which is the same as 2U minus V, just written in a different, writing 2U first. So any one of those will give you your 1 mark. And then finally, part 2 says to show that MN is parallel to PR. So a teaching point here is that parallel vectors, so this is a note, right? Parallel vectors are scalar multiples. Parallel vector, and show you what I mean by scalar multiples, right? So parallel, so think about, I'm just going to write it like this. Parallel vectors means that they are scalar multiples. So for example, a scalar multiple is like if you have a vector, so like an example would be, guys, if you have a vector A, the vector AB is equal to, and I'm writing this in vector notation, right? In the, like this, 2, 3, right? So if I have a vector AB is equal to 2, 3, then a scalar multiple, right? Scalar multiple, let's say I have another vector, CD is equal to 4, 6. Do you realize that 4, 6 is really just, to get 4, 6 is really just multiplying 2, 3 by 2, right? Because CD, if CD is 4, 6, then 2 times 2, 3 is equal to 2 times 2 is 4, and 2 times 3 is 6. So in other words, therefore, I can say that CD, the vector CD, is really 2 times the vector AB. And since CD is 2 times AB, we say that CD is a scalar multiple of AB. It just means that if I multiply AB by one scalar, then in this case it's 2, I get the resultant vector CD 4, 6. So that means that CD is a parallel vector to AB. That's what parallel vectors are. Parallel vectors are scalar multiples. So they could have a third vector. Let's say I have a third vector, EF, right? So let's say I have a third vector, EF. And let's say this vector is equal to 6, 9. This is also a scalar multiple of 2, 3 because 6, 9 is really 3 times 2, 3. So it makes EF a scalar multiple of AB. All right, let me see. Let me take a little check-in here. Who is here? Let me see. Aaron, can you hear me? Because I'm seeing you on here, but just now when I saw that you typed, so I was wondering if your mic is working. Doubt. Jazara. What would be like, can you give me an example of another scalar multiple of AB? Like how 4, 6 is a scalar multiple of AB because I just multiplied AB by 2. What could be another scalar multiple of AB?
Oh, it's only 10:52
Yeah, what you multiply by?
by 5.
Mm-hmm. Right? So if you have another, if you multiply 2, 3 by 5, right? Like Jazara just said, if I multiply 2, 3 by 5, I'll get 10, 15. And this vector will be a scalar multiple of AB, and so it will be a parallel vector to AB. So when you have a question that is asking you to show that two vectors are parallel, right? To show that MN is parallel to PR, what you need to show is that one of them is a scalar multiple of the other, right? Which means that if you multiply, like we know what MN is, right? MN is minus U plus V. So if I multiply minus U plus V by some constant, right, or some scalar, it would be a scalar multiple of NM. So sorry. So I need to show that PR is a scalar multiple of MN. So firstly, we need to find what PR is equal to. Now, PR, remember, when you are trying to write an expression for PR is the vector from starting at P and ending at R. So PR is this vector that I just showed here in red. So to get PR, I can add PO plus OR, and that would give me PR, right? And I can do that easily because PO will just be the opposite of OP, and I already know that OP is 2U, so PO will be minus 2U. And then OP, well, OP is just 2V. So let's write that down, right? PR will be equal to PO plus OR. Also very, very important to note. Okay, so that's part 2, right? PR, the vector PR would be equal to PO plus OR. Remember, it has to start and end with, well, it has to start with P and end with R. And also these 2 points, it has to be from the origin, right? It has to, well, it doesn't have to be from the origin. It just has to be a common point. It's one continuous movement, right? So you have PR, P was here and R was here. It's in this direction. So to get PR, I will add this vector, PO, plus this vector, OR. And OP is 2U. So therefore, PO will be equal to minus 2U. And OR will be equal to 2V because this is V and this is V. So V plus V is 2V. right? So the vector PR is equal to minus 2u plus 2v. And look, what I can do here is I can factor this out because I could factor the 2 out because I have a common factor of 2 here. So writing this in factorized form, I would write 2 on the outside. 2 by minus u will give me minus 2u, and 2 by v gives me 2v. So this is PR can be written as 2 times minus u plus v. And if we go back to question 1, part A, mn is equal to minus u plus v. So therefore, PR is the same as saying 2 times mn. Therefore, PR, okay, before I write that, let's recall that mn is equal to minus u plus v. So therefore, PR is equal to 2 times the vector mn. And so therefore, PR is parallel to mn because you just simply multiply mn by a constant or a scalar and you get what PR is equal to. So this is how you would do any question where they're asking you to show that that another vector, like two vectors are parallel. To show that two vectors are parallel, you must show that they are scalar multiples of each other. Okay. All right. So that is basically a few very important things to know about vectors. Let's move on to the matrices part of this question. So question B, 10B, this is from your question 10, January 2026, right? The matrix P written in terms of A, where A is a real constant, is as follows. P is equal to 3A, 4, and 6, 2A. So it's a 2 by 2 vector because you have 2 rows, 1, 2, and 2 columns, right? So this is a 2 by 2 vector. Part 1 tells us to calculate the determinant of P in terms of A. So let's recall what the determinant of a vector is. So this is something to note. The determinant of a vector, let's say the vector is A, right? And let's say A is A, B, C, D. To find the determinant of this, you simply minus the products of the diagonals. So it will be A times D minus B times C. That's how you find the determinant of any vector. So if you have a vector A, B, C, D, the determinant will be A times D minus B times C. So let's use a one that has numbers, right? So let's say I have a vector, and this vector is 2, 3, 6, 7, right? What I would do is to find the determinant here. So let's say this is the vector B. This is the vector B, right? And I want to find the determinant of B. Let's say I want to find the determinant of B. The determinant of B will be equal to 2 times 7, right? The products of the diagonals, the difference of the products of the diagonals. So it will be 2 times 7 minus 3 times 6. So this will be 2 sevens are 14 and 3 times 6 is 18. So the determinant of this vector B will be 14 minus 18, which is negative 4. So that's how you find the determinant of any vector, of any matrix, any 2 by 2 matrix. And for the sake of CSEC math, you only need to do 2 by 2 matrices. All right, so to calculate the determinant of P in terms of A, looking at this question, right, let's just rewrite the vector. P is equal to 3A, 4, 6, 2A, right? So therefore, the determinant of P would be the product of the diagonals, the difference of the products of the diagonals. So 3A times 2A, 3A times 2A minus 4 times 6. So this would be 3A times 2A. 3 times 2 is 6, and A times A is A squared, minus 4 times 6, which is 24. So this is the determinant of P in terms of A. It's going to be 6A squared minus 24. And now part B, determine the values of A for which the matrix P is singular. This is a common question, and what we need to know here is what is meant by a singular matrix. So the teaching point here, or the learning point for you, is that a singular matrix is a matrix whose determinant is 0. So a matrix is singular if its determinant is 0. So if its determinant is equal to 0. All right. So determine the values of A for which matrix P is singular. So if I have to do that, I would have to show that the determinant of P is equal to 0. So from 1, so this is part 2 now, right? And from part 1, we got what the determinant is. So from part 1, the determinant of P was equal to 6A squared minus 24. So if P is a singular, then it means if P is singular, then the determinant of P is equal to 0. So in other words, 6A squared minus 24 is equal to 0. And I can solve for A here because I can use, well, first I could divide throughout by 6, and that would give me A squared minus 4 is equal to 0 divided by 6, which is 0. And then if A squared minus 4 is 0, then A squared is equal to 0 plus 4. And then if A squared is equal to 4, then A would be the square root of 4. So A would be plus or minus 2. Remember, the square root of any number is positive or negative. All right, and just to show you why this would make sense, if A was positive 2, it's saying that the determinant would have to be, well, if it's singular, the determinant will be 0, right? So let's substitute A is 2 into the matrix. So the matrix is 3A, 4, 6, 2A. That's the matrix P, right? So if A is 2, then that means this will be 3 times 2, which is 6. And then on the bottom, 2 times 2, which is 4, right? And then the determinant of this would be 6 times 4 minus 6 times 4. So 24 minus 24, which is 0. So it does work out there. And even if it was negative 2, well, then this would have been negative 6 by negative 4. So then you'll have 6 negative 6 times negative 4, which is positive 24. Take away 24, which is also 0. So this confirms that our answer is correct. So just to recap the important things that you need to know here. And guys, you know what? I would suggest writing this down in your books, okay? I will send you this whole thing afterwards. And I would suggest writing it down because it's a nice, it covers so much that you need to know for these types of vectors and matrices questions, right? Good. So far in terms of the matrices, we recall that the determinant of any matrix, any 2 by 2 matrix, is the difference of the products of the diagonals. What do I mean? by that, you multiply, you find, just draw do a diagonal circle like this. I find that helps me. Like say this, AD minus BC. That gives you your determinant, right? So therefore, if you have a matrix, A is equal to ABCD, then A would be AD minus BC. All right. In this case, we had to calculate the determinant of P, the matrix P that was given in terms of A. So it was 3A times 2A minus 4 times 6, which was 6A squared minus 24. All right. The next part of the questions, what we looked at is what is a singular matrix? A matrix is singular if its determinant is equal to 0. All right. And finally, part 3 now, determine P inverse, well, P to the power of -1, which is the inverse of P, for which P is non-singular. So this gives me a moment to refresh your memory on how we determine the inverse of a matrix. So the inverse of a matrix, let's say a matrix, I'm going to put this in red so that you know it's a note, right? The inverse of a matrix, let's say we have a matrix A is equal to A, B, C, D, right? Then A inverse is equal to 1 over the determinant of A multiplied by what we call the adjoint of A. So we already know what the determinant is. We know how to find the determinant of A. The adjoint, right? A adjoint is equal to, this is where you swap the first and last terms. So instead of A, I'll put D there, and I'll put A as the end, and I change the signs of the remaining ones. So I don't swap those remain as B and C, but I change their signs. So it will be negative B and negative C. This is A adjoint, right? So therefore, the determinant, right? Therefore, the A inverse will be 1 over the determinant of A. Let me just write back what is the determinant of A. The determinant of A will be A times D minus B times C. So the inverse of A then is 1 over this. That's AD minus BC multiplied by the adjoint of A, which is D minus B minus C A. You have to memorize this, guys. This is not given to you in the list of formulae. You have to memorize these things. So you have to know this. And then, of course, you would need to know what's the determinant of A and what is A adjoint. Right? So let's look at an example, and then let's do an example with actual numbers, and then we'll do this part of the question that says to determine P inverse, right? Now notice that it says for which P is non-singular. In order for P to be non-singular, it means that if singular means the determinant is 0, then non-singular means that the determinant is not equal to 0. Because if you can only find the inverse, and this is important, right? This is actually important. You can only find the inverse. You can only find the inverse of a non-singular matrix. You cannot find the inverse of a singular matrix, or actually, better yet, you can learn it as the fact that only non-singular matrices have inverses. And it would make sense because if a singular matrix is where the determinant is zero, right? Remember, you can't divide by zero, so you can't have 1/0. That's like that you'll get an error, right? That does not exist. You cannot divide by zero. So that's why you can only find the inverse of a non-singular matrix, or that non-singular matrices have inverses. Only non-singular matrices have inverses. Singular matrices do not have inverses. All right, so let me show you guys an example. Let me zoom out a little bit. All right, so say we have, this is an example, right? Let's say we have the matrix C is equal to 1, 4, 5, -2. Right? That's my matrix C. So if I have to find C inverse, I would need to recall. So let's recall that C inverse is equal to 1 over the determinant of C multiplied by C adjoint. All right. By the way, the determinant of a matrix can also be written like this. So the determinant of C can also be written as like this, like the absolute value of C. All right, so let's first determine what is the determinant. Determinant. Anyway, let's find the determinant of C and then write C adjoint. Okay, so C, the determinant of C. Oh, the pen isn't working. Give me a second. Oh, I had one erase. Right, so the determinant of C, remember, it's the product, the difference of the products of the diagonals, right? So this will be 1 times -2. Take away 4 times 1. 4 times 5, sorry. 4 times 5. So this is equal to 1 times -2 is -2. Take away 20. So that's -22. That's the determinant of C. So therefore, C inverse will be 1 over -22, which will really be -1 over 22 by C adjoint, right? So C adjoint is where you swap the first and last one. So this will be -2, 1, and then this will be -4, -5, right? So it'll be -1 over 22 multiplied by -2, -4, -5, 1. And you can leave it like this, or you can actually simplify it, right? So simplifying means that I'm just going to multiply this scalar throughout. So when you're multiplying a matrix by a scalar, you simply multiply every element in the matrix by that scalar. So I'll multiply -2 by -1 over 22, which will give me 2 over 22, which is 1 over 11. So the first term here will be 1 over 11. -4 times, you know what, let me write this out fully before it confuses anybody. I just simplify the fraction, right? But anyway, -2 times -22 will be +2 over 22. -4 times -1 over 22 will be 4 over 22. -5 times -1 over 22 will be positive 5 over 22, because when you multiply two negatives, you get a positive. And then finally, +1 times -1 over 22 will be 1 over 22. So this, written in a simplified way, will be 1 over 11, 2 over 11, 5 over 22, and 1 over 22. And that is my C inverse, right? So that's how you find the inverse of a matrix. You have to know this, guys. It comes very often, so you need to know it. And then, so now that we know, or we have refreshed our memories on the inverse of a matrix, let us now find the inverse of P. for which P is non-singular. So guys, it means that if P is non-singular, we cannot substitute this value 2 into P, right? Because then that would make this matrix a singular matrix. So it means then that we simply need to write the inverse of P in terms of A, right? In terms of how it's given right here. So we have, let's just rewrite P, right? So P, this is part P. P, I'm going to use a different color just so that we don't get mixed up. Right. So P is equal to 3A, 4, 6, and 2A. So recall that P inverse will be 1 over the determinant of P by P adjoint. We already know what the determinant of P is. We found that up here, right? The determinant of P is 6A squared minus 24. So that would be, therefore, P inverse is equal to 1 over 6A squared minus 24 by P adjoint. So P adjoint will be where we swap the first and last ones. So this will be 2A, 3A, right? I'm switching 2A and 3A, the positions of those two, and I'm changing the signs of the remaining elements. So this here is the inverse of P. And I believe that this will be fine. I believe that you can leave it just as is there. Now you can simplify it if you want. I'm going to write the simplification if you want. You don't need to. I don't think you need to. But that would be, if I were to simplify this, right, then, well, first of all, 1 over, I could factorize this. So that would be 6 by A squared minus 4, right? 6 into A squared is 6, and 6 into minus 24 is 4. So that would be on the outside there. And if I were to multiply that by 2A minus 4 minus 6 and 3A, right? Then that would mean 2A times this whole thing would be 2A over 6 by A squared minus 4. Minus 4 times that will be minus 4 over 6 by, guys, this is, you don't need to do this part. I'm pretty sure that this is fine. I'm just showing you what you would get if you simplified it anyway. And then down here you'd have minus 6 over 6 by A squared minus 4, and then 3A over 6 by A squared minus 4. All right, so simplifying this whole thing, this is what would happen. You could cancel, right? You can cancel. You can say 2 into 2 is 1, and 2 into 6 is 3. 6 into 6, 1, 6 into 6, 1. 2 into 4 is 2. 2 into 6 is 3. 3 into 3, 1. 3 into 6, 2. So the final answer here would be A over 3 by A squared minus 4. 2 over 3 by A squared minus 4. 1 over A squared minus 4. And A over 2 by A squared minus 4. I don't believe that you needed to do all of this to get your 2 marks, right? I'm pretty sure that this part here would, up till here, would give you your 2 marks, right? But I'm just showing you that you can multiply the scalar 1 over the determinant by each element inside. All right, so let us look now at part C. Now, part C is the transformation matrices question. It says, write down the 2 by 2 matrix that represents a counterclockwise rotation of 90 degrees about the origin and label this matrix X. So transformation, guys, transformations have to do with things like a reflection, a rotation, that kind of stuff, right? Or enlargement. And we have certain matrices for each of those. So the first one, a counterclockwise rotation of 90 degrees about the origin. That would be, so, and they said to label that matrix X, right? So X is equal to the transformation matrix that represents a a counterclockwise rotation of 90 degrees about the origin is 0, -1, 1, 0. So let's take this moment to review all the different transformation matrices, right? So the different transformation matrices, guys. All right. So the first one we have, and all of these are anti-clockwise, right? So you have, and you have to learn these off, by the way. You have to learn these off by heart. So a counterclockwise rotation of 90 degrees about the origin. This matrix is given as 0, -1, 1, 0, right? You can have a counterclockwise rotation of 180 degrees, right? So counterclockwise means anti-clockwise, right? Oh gosh, what am I writing there? Clock, like a chicken. Clockwise rotation of 180 degrees about the origin. So all of these that I'm writing here are about the origin. This is given as the matrix -1, 0, 0, -1. Right? You have to learn these guys, right? I'm giving you the main ones. You have a reflection in the x-axis, a reflection in the x-axis is given as the matrix 1, 0, 0, -1. Right? So that's like if you have like let's say just let's put this into perspective here. If you have this is your y-axis, this is your x-axis, right? If we're looking at a reflection, so this is your x-axis here, and this is your y-axis. If we're looking at a reflection in the x-axis, it means like if you have a point over here, a reflection in the x-axis, you'll reflect it over, you'll put it here. So if this is A, our reflection in the x-axis will give you A prime, right? So let's say if this point here, the coordinates of this point is, let's say this is 1 and this is 1, right? The coordinates of A here is -1, 1, right? -1, 1. A reflection in the x-axis would give you the resultant point, still -1 as the x coordinate, but the y coordinate will be -1 instead of 1, right? So a reflection in the x-axis changes the sign of the y coordinate because above the x-axis, y is positive, and below the y-axis, below the x-axis, y is negative. So any point, if you reflect it in the x-axis, the x-coordinate would remain the same, but the y-coordinate will change. And that's why it is the matrix that represents a transformation of a reflection in the x-axis will be 1, 0, 0, -1. And let me show you just a step further. If I didn't do the diagram and I wanted to find out what is the resultant point, A prime, when I reflect A in the x-axis, I can multiply the matrix 1, 0, 0, -1 by 1, 1. All right, so that would be 1, 0, 0, -1 times the point A, which is negative 1, 1. And look what I will get. So you do row by column, 1 by negative 1 times 0 by 1. So 1 times negative 1 is negative 1 plus 0 times 1 is 0. So this will be negative 1. And then row by column again, 0 by negative 1 is 0. And negative 1 by positive 1 is negative 1. So you see how I got it? When I multiply the transformation matrix by the points, I got negative 1, which is correct because I just showed you that here, right? So when you multiply a transformation matrix by a point, you'll get the resultant matrix, right? So the transformation that represents a reflection on the x-axis is 1, 0, 0, 1. Now, you can also have a reflection in the y-axis. And if you think about what happens with the y-axis, to the left of the y-axis, x is negative, and to the right of the y-axis, x is positive. The transformation that represents a reflection, let me write out the word and stop being lazy. The matrix that represents a reflection in the y-axis is negative 1, 0, 0, 1. Right? So let's look at that in terms of the x and y axes. So if you have this is your y-axis, it's the vertical axis, and you have your x-axis, that's the horizontal axis. So this is your y and this is your x, right? If I have a point, let's say this point here is B, and the coordinates of this point is 3, 4, right? So that's the coordinates of the point B, 3, 4. If I were to reflect that point B in the y-axis, let's say it's here, and this is just a sketch, so it's not drawn to scale, and this is my point B prime, I would expect it's going to be the same distance away from the origin here on the left side of the y-axis. So this will now be, this point would actually be negative 3, 4. The y is still the same, right? But the x is different. So if I multiplied the transformation matrix negative 1, 0, 0, 1 by the point B, which is 3, 4, I should get B prime, which is negative 3, 4. And let me show you, right? So let's see. The transformation that represents the reflection in the y-axis is negative 1, 0, 0, 1. So that would be negative 1. And notice how I am writing the transformation matrix in front of the point, right? It's because the point is a 2 by 1 matrix, and matrix multiplication has to have the same number of rows in the same number of columns, sorry, in the first matrix must be equal to the number of rows in the second matrix. So let's see what that would give us. It's negative 1, 0, 0, 1. So I already know what I'm supposed to get, right? I'm supposed to get negative 3, 4. So multiplying negative 1, 0, 0, 1 by 3, 4 gives me, well, negative 1 times 3 is negative 3 plus 0 times 4 is 0. So this will be negative 3. And then 0 times 3 is 0 plus 1 times 4 is 4. So you see how I got it, right? It's the same thing. So that's what transformation matrices are. It's not arbitrary things that you're learning. You have to make the connections, all right? And making connections is what helps you to get better in math, guys. The persons who can see the most connections between the topics that they're learning in math are the students who become strong, right? Because math is all about patterns and connections. So the reflection in the y-axis is given by the matrix 1, 0, 0, negative 1, while the transformation matrix that represents a reflection in the y-axis is negative 1, 0, 0, 1. you also have a reflection in the line y is equal to x. So a reflection in the line y is equal to x. What happens in this is that you swap x and y, right? I'll show you what I mean. So this, let's say this is going to be 0, 1, 1, 0. Now, the line y is equal to x is a vertical line passing through the origin. So if you have this is your y-axis and this is your x-axis, right? The line y is equal to x is a a diagonal line passing through the origin like this. Right? That is your line y is equal to x. Y is equal to x. So what happens when you reflect a point in the line y is equal to x? Let's say you had a point here, right? And this point is, let's say this point is 7, 1, right? Then if I reflect that point in the line y is equal to x, it's going to be probably like here, right? Because you remember, reflecting is like a mirror line, okay? And the coordinates of this point will now be 1, 7. Do you notice what happened here? The x became the y and the y became the x. So you swap the positions of the point. You swap the points basically. X becomes y and y becomes x. That is what happens when you reflect a point in the line y is equal to x. So let's put it to the test. Let's say this is A and I reflected it in the line y is equal to x and this is A prime. So if A is 7, 1, A prime will become 1, 7 using the matrix multiplication, right? And multiplying 0, 1, 0, 1 by 0, 1, 1, 0 times the point 7, 1, right? This will give me, you do row by column and then row by column. So 0 times 7 is 0 and 1 times 1 is 1. And then 1 times 7 is 7, 0 times 1 is 0. So this will be 1, 7. And look, right? That's what I got here. This is A prime. And this is A, right? So this is what it means for me. This is what matrix transformations represent. They represent real transformations in the Cartesian plane. So when you're thinking of it, try to visualize it in your head, right? And then you can also, just like you have the reflection in the line y is equal to x, you can also have a reflection in the line y is equal to negative x, right? So you can also have, you can also have a reflection in the line y is equal to negative x. And that is given by 0, negative 1, negative 1, 0. So it's exactly like y is equal to x, except it's negatives instead. And the line y is equal to negative x, guys. Well, if this is your y-axis and this is your x-axis, the line y is equal to negative x will be a diagonal line in the other direction. So this one is your line y is equal to negative x. It's the same principle. And then the last transformation that I think is important for you to know is enlargement, right? An enlargement. An enlargement, as the name suggests, is when you enlarge a shape. So, for example, if I have a shape, let's say I have this square, right? Then an enlargement of this square will be the same square, but bigger, right? That's what an enlargement is. So the matrix transformation that represents, the matrix that represents an enlargement. So this is an enlargement with the center, with the origin as the center. So with center 0, 0. and a scale factor of K is represented by the matrix K, 0, 0, K. Right, so you just multiply the matrix by whatever the scale factor is. All right, guys. So now you have to memorize these. You have to memorize the different matrix transformations. So I'll tell you I find the ones that you kind of have to memorize. You just need to look for like the y-axis and the x-axis and the line y is equal to x. You really just need to know one, because if you know what the reflection in the x-axis is, then you would be able to tell what's the reflection in the y-axis, because it's just the opposite, right? And it's the same for the reflection in the line y is equal to x and y is equal to negative x. So like the reflection in the x-axis is 1, 0, 0, negative 1, right? And therefore the reflection in the y-axis will be negative 1, 0, 0, 1. So you see it's the opposite, right? Because like I showed you, when you reflect in the x-axis, y becomes you change the sign of y. When you reflect in the y-axis, x is the one that the sign changes, right? In the line y is equal to x, it will be 0, 1, 1, 0. So then the reflection in the line y is equal to negative x is the opposite. So it's negative. So you see, you don't have to learn them often. You don't have to learn them in isolated ways. Look for connections to help you memorize them. I don't know what connection I could give you for the counterclockwise ones in like of 90 degrees or of 180 degrees. I'm not really sure about those. Oh, actually, the counterclockwise, I forgot to give you one of the rotations, the rotation of 270 degrees. The rotation of 270 degrees is the same as basically clockwise. Well, it's like minusing. Never mind, actually. Let me not say that to confuse you. The counterclockwise rotation of 270 degrees is 0, 1, negative 1, 0. So it's like the 90 degree, except this one is negative. Let me write it down and show you. I wish I could have written it right there, but if I were to erase all of this, I'll have to write it over. So the counterclockwise rotation of 270 degrees about the origin is given by 0, 1, negative 1, 0. All right, it's similar to the 90 degree, because the 90 degree is 0, negative 1, 1, 0. So it's the opposite of the 90 degree one. And I mean, it does kind of make sense, because if you think of a 90 degree, right? A 90 degree angle is from here to here, right? This is true 90 degrees. This will be 90 degrees, right? 270 degrees is going to take you here. But I could get to the same point. I could get to the same point by just coming here as well, right? By going 90 degrees in the opposite direction. So it's kind of like the same thing. 270 degrees is the same as going in the opposite direction of 90 degrees. Hopefully that makes sense to you. Right. So guys, you have to learn these, right? Sometimes they give you a piece of it. So like, for example, in this question, it says to write down a 2 by 2 matrix that represents a counterclockwise rotation of 90 degrees about the origin, followed by a reflection in the y-axis, given that Q, which is negative 1, 0, 0, 1, represents the reflection in the y-axis. So they gave you what the matrix is here. Sometimes they don't. Sometimes you have to tell us what it is, like in part 1, which asked you to write the 2 by 2 matrix that represents the rotation, the counterclockwise rotation of 90 degrees. So when you have to combine a pair of transformations, so in this one, it's 2 transformations that we're undertaking. We're first doing a counterclockwise rotation of 90 degrees, and we're following that up with a reflection in the y-axis, right? And this matrix is equal to T. Now, let me tell you, if the counterclockwise rotation of 90 degrees is X, right? So let me write this out. See if I could put this side by side. Yes, I can. Right. So if X is the, I'm not writing properly at all today. Just now, guys. Give me 1 second. Right. So for this is part 2, right? This is part 2. So we're going to recall that X, the counterclockwise rotation of 90 degrees, is equal to 0, negative 1, 1, 0. That's the counterclockwise rotation of 90 degrees. This is your counterclockwise rotation or anti-clockwise rotation of 90 degrees, right? About the origin. And now they gave us that Q is equal to negative 1, 0, 0, 1. And this transformation is a reflection in the y-axis. Reflection in the y-axis. Well, if I want T, the singular matrix that represents, so if T is the matrix that represents a counterclockwise rotation that represents X followed by Q, that is the counterclockwise rotation of 90, followed by a reflection in the y-axis. Guys, this is very important. T is equal to, you write the last thing. So if it's X followed by Q, X goes here and Q goes here, right? Now, that is kind of counterintuitive because you would expect that if you're doing X followed by Q, most students would say, oh wait, I wrote this wrong. This is the wrong thing I wrote, sorry. If it's X followed by Q, it's going to be QX, right? In like just looking at it, you would think it's going to be XQ, which is what I just wrote, which was wrong, right? Because you would say, well, X followed by Q, you write X first and then Q. But when you're doing transformation matrices, when you're writing a combination of matrices, of transformation, sorry, you put the first one goes on the right and the last thing comes on the left, right? So if it's a reflection in it's a rotation of 90 degrees followed by a reflection in the y-axis, it means it is X followed by Q. So X goes on the right-hand side and Q comes on the left side. Please, please, please make a note of that. And it will be wrong if you did it in the opposite way, right? Because matrix multiplication is not commutative. So QX is not equal to XQ. So it does matter how you write it. It does matter the order of the operation in this case, right? Matrix multiplication, unlike regular multiplication, is not commutative. So when you are doing a combination of transformations, you have to, in your head, just know that is the opposite. That is the opposite way that you're writing it, right? So in this one, if it's the rotation followed by the reflection, the rotation will go on the right and the reflection will come on the left. If, however, it was a reflection followed by the rotation, it would be XQ, right? So this matrix will have to, it's a singular matrix that we're writing out, right? It's a 2 by 2 matrix. So we need to do the matrix multiplication here. So T will be equal to Q, which is -1, 0, 0, 1, multiplied by X, which is 0, -1, 1, 0. Right? So recall your rules of matrix multiplications. It's row times column, row times column. Guys, if you cannot remember these things, please go and watch the videos on matrix multiplication. I have several of them, and there are so many on YouTube, but you need to know your matrix multiplication, right? So to multiply your matrices, you do row times column. So row 1 times column 1 for your first position here. So that'll be -1 times 0, which is 0, plus 0 times 1, which is 0. And then for this position, row 1, column 2, you're going to do row 1 times column 2. So -1 times -1 is +1, plus 0 times 0 is 0. So +1 goes here. And then for this position, your third position here, right? That third position is your row 2, column 1, sorry. So you're going to multiply row 2 by column 1. So row 2, 0 times 0 is 0, plus 1 times 1 is 1. So that's 1. 1 goes there. And finally, your final position, which is row 2, column 2, you're literally going to multiply row 2 by column 2. So 0 times -1 is 0, plus 1 times 0 is also 0. 0 plus 0 is 0. And this is your matrix T that represents a rotation in the a rotation in the a rotation of 90 degrees about the origin, followed by reflection in the y-axis. It's 0, 1, 1, 0. And that is your answer for your 2 marks. And guys, if you notice, this matrix is actually a reflection in the line y is equal to x, 0, 1, 1, 0. But they didn't ask you to describe it. They just asked you to write the matrix T. Right? Now, if they had asked you to describe it, what does this matrix represent? You would have to say that this matrix is a reflection in the line y is equal to x. So this matrix is actually a reflection in the line y is equal to x. But that was not us. So you didn't need to do that. All right. Guys, we're going to stop there for today.